Welcome to our deep dive into the science behind time travel. For centuries, humans have been fascinated by the idea of moving through time, whether to revisit the past or glimpse the future. From ancient myths to modern movies, time travel has captured our imagination. But is it just science fiction, or is there real science that could make it possible? In this video, we'll explore the theories, experiments, and scientific principles that underpin the concept of time travel. Get ready to journey through the mysteries of time itself as we unravel what science says about bending the very fabric of reality. Before we can understand time travel, we need to define what time actually is. Time is often described as the fourth dimension alongside the three dimensions of space. It's a way to measure the sequence of events and the intervals between them. In physics, time is a fundamental quantity, but its true nature remains one of the biggest mysteries. Is time an illusion, or is it a real, tangible part of our universe? Scientists continue to debate this, but most agree that time is closely linked to the fabric of space itself, forming what we call spacetime. One of the most important scientific breakthroughs related to time travel is Albert Einstein's theory of relativity. According to Einstein, space and time are intertwined in a single continuum called spacetime. His equations showed that time is not absolute. It can stretch or shrink depending on how fast you're moving or how strong gravity is. This means that time can pass at different rates for different observers, a phenomenon known as time dilation. This concept is key to understanding how time travel might be possible, at least in theory. Time dilation is a fascinating consequence of Einstein's relativity. If you travel close to the speed of light, time slows down for you compared to someone who is stationary. This has been confirmed by experiments with atomic clocks on fast-moving jets and satellites. Astronauts aboard the International Space Station, for example, age just a tiny bit slower than people on Earth. While the effect is minuscule at everyday speeds, it becomes significant as you approach the speed of light. This opens up the possibility of traveling into the future, at least from the perspective of those left behind. Gravity doesn't just keep us anchored to the Earth, it also affects the flow of time. According to general relativity, the stronger the gravitational field, the slower time passes. This has been demonstrated by placing precise clocks at different altitudes. Clocks closer to the ground, where gravity is stronger, tick more slowly than those higher up. This effect, known as gravitational time dilation, is crucial for technologies like GPS, which must account for these tiny differences to provide accurate location data. Is time travel to the future possible? According to the laws of physics, yes, at least in a limited sense. By traveling at speeds close to light or spending time in a strong gravitational field, you could experience time more slowly than people elsewhere. When you return, you'd find that more time has passed for everyone else. This is called time dilation-based time travel, and while it's not the dramatic leap seen in movies, it's a real effect observed in experiments and in space travel. Famous thought experiment that illustrates time dilation is the twin paradox. Imagine two twins, one stays on Earth while the other travels into space at near light speed and then returns. The traveling twin would have aged less than the one who stayed on Earth. This isn't just a theoretical idea. Experiments with fast-moving particles and precise clocks have confirmed that time really does pass differently depending on your speed and gravity. Beyond time dilation, some scientists have proposed the existence of wormholes, hypothetical tunnels that connect distant points in spacetime. If wormholes exist and could be stabilized, they might allow for shortcuts between different times or places. The idea comes from Einstein's equations, but so far wormholes remain purely theoretical. It would require exotic matter with negative energy to keep them open, something we haven't discovered yet. Black holes are some of the most extreme objects in the universe, with gravity so strong that not even light can escape. Near a black hole, time slows down dramatically compared to regions farther away. This effect, predicted by general relativity, has been observed indirectly through the behavior of matter near black holes. Some theories suggest that black holes could even act as gateways to other times or universes, though this remains speculative. Another theoretical concept involves cosmic strings, thin, high-energy defects in spacetime that may have formed in the early universe. Some physicists believe that if two cosmic strings pass close by each other, they could warp spacetime enough to create closed time-like curves or time loops. These loops could, in theory, allow for travel to the past. However, cosmic strings have never been observed, and the idea remains highly speculative. One of the biggest challenges with time travel to the past is the grandfather paradox. This thought experiment asks, what happens if you travel back in time and prevent your own grandfather from meeting your grandmother? Would you cease to exist? This paradox highlights the logical contradictions that arise when considering backward time travel and has led many scientists to question whether it's truly possible. Resolve time travel paradoxes. Some scientists propose the multiverse theory. This idea suggests that every possible outcome creates a new, parallel universe. So if you travel back in time and change something, you'd simply create a new timeline, leaving your original history intact. While the multiverse remains unproven, it offers a way to sidestep the logical problems of time travel to the past. Quantum mechanics, the science of the very small, introduces even more strange possibilities for time travel. Some interpretations of quantum theory suggest that particles can exist in multiple states at once, and that the act of observation can affect their past behavior. While this doesn't mean we can send people back in time, it does hint at a universe where time is less rigid than we once thought. Closed time-like curves, or CTCs, are solutions to Einstein's equations that allow for paths through spacetime that loop back on themselves. In theory, traveling along a CTC could let you return to your own past. However, creating or finding such curves would require conditions far beyond anything we can achieve, and there are many unresolved questions about whether they could exist without causing paradoxes. Physicist Stephen Hawking proposed the chronology protection conjecture, which suggests that the laws of physics prevent time travel to the past. According to Hawking, quantum effects would destroy any time machine before it could be used, preserving the consistency of history. While this idea is still debated, it highlights the challenges of reconciling time travel with the known laws of physics. Time travel has been a staple of science fiction for decades, inspiring countless books, movies, and TV shows. From H.G. Wells' The Time Machine to Back to the Future and Doctor Who, these stories explore the possibilities and dangers of moving through time. While the science often takes a back seat to storytelling, these works have sparked real scientific curiosity and debate. Scientists have conducted real-world experiments to test the predictions of relativity and time dilation. For example, atomic clocks flown on airplanes have shown measurable differences compared to those left on the ground. These experiments confirm that time really does pass differently depending on speed and gravity, supporting the idea that time travel to the future is possible, at least in a limited way. Global Positioning System, or GPS, relies on a network of satellites orbiting Earth. These satellites experience both special and general relativistic effects, causing their clocks to tick at different rates than those on the ground. Engineers must account for these differences to ensure GPS accuracy. Without these corrections, GPS would quickly become useless, highlighting the real-world impact of time dilation. While traveling to the future is supported by physics, going back to the past is much more problematic. The laws of thermodynamics, causality, and the potential for paradoxes all stand in the way. Most scientists believe that backward time travel is either impossible or would require conditions and materials that don't exist in our universe. For now, the past remains out of reach. The arrow of time refers to the one-way direction in which time seems to flow from past to future. This is closely linked to the second law of thermodynamics, which states that entropy or disorder always increases over time. This gives time its apparent direction and makes revering it extremely difficult, if not impossible, according to our current understanding. Causality is the principle that cause comes before effect. Time travel to the past threatens this order, potentially allowing effects to precede their causes and creating logical inconsistencies. Many physicists argue that the universe has built-in mechanisms to prevent such violations, ensuring that history remains consistent and paradox-free. Theoretical models of time machines require exotic matter, substances with negative energy density. This exotic matter could, in theory, stabilize wormholes or create closed time-like curves. However, no such material has ever been observed, and it's unclear whether it could exist in our universe. Without exotic matter, building a time machine remains firmly in the realm of science fiction. According to Einstein's theory, nothing with mass can travel faster than the speed of light. This speed limit is a major obstacle for time travel, as many proposed methods require moving at or beyond light speed. Breaking this barrier would require infinite energy, making it impossible with our current technology and understanding of physics. Tachyons are hypothetical particles that always move faster than light. If they exist, they could, in theory, allow for communication or travel backward in time. However, there is no experimental evidence for tachyons, and their existence would violate many known laws of physics. For now, they remain a fascinating but unproven idea. Time travel to the past introduces a host of paradoxes, such as the grandfather paradox and the bootstrap paradox, where an object or information exists without a clear origin. These logical puzzles challenge our understanding of cause and effect and suggest that backward time travel may be fundamentally impossible. Entropy, a measure of disorder, plays a crucial role in the direction of time. The second law of thermodynamics states that entropy always increases, giving time its arrow. This makes revering time or decreasing entropy extremely unlikely and is one of the main reasons why time travel to the past is so problematic. Quantum entanglement is a phenomenon where two particles become linked, so that the state of one instantly affects the other, no matter how far apart they are. Some researchers have speculated that entanglement could be related to time travel or communication across time, but so far there's no evidence to support this. It does, however, show that the universe is stranger than we ever imagined. Block universe theory suggests that past, present, and future all exist simultaneously in a four-dimensional block of spacetime. In this view, time is just another dimension and all events are fixed. While this idea is controversial, it offers a different perspective on time and raises interesting questions about free will and the possibility of time travel. Some science fiction stories feature faster-than-light travel like warp drives or hyperspace jumps. While these ideas are exciting, they face enormous scientific challenges. According to our current understanding, nothing can exceed the speed of light, and doing so would violate causality and the laws of physics. For now, faster-than-light travel remains a dream. Alcubierre drive is a theoretical concept that involves compressing space in front of a spacecraft and expanding it behind, creating a warp bubble that could move faster than light without violating relativity. This idea requires exotic matter and enormous energy, making it far beyond our current capabilities. Still, it shows how creative scientists can be when imagining ways to travel through time and space. Even if we can't send people through time, could we send information? Some theories suggest that quantum entanglement or hypothetical particles could allow for messages to be sent backward in time. However, this would still face the same paradoxes and challenges as physical time travel, and there's no evidence it's possible. If time travel were possible, what would it mean for free will? Would our actions be predetermined, or could we change the past? Philosophers and physicists have debated these questions for decades. Some theories suggest that the universe would prevent any changes that create paradoxes, while others propose that every choice creates a new timeline. Novikov's self-consistency principle is a proposed solution to time travel paradoxes. It states that any actions taken by a time traveler were always part of history, so paradoxes can't occur. In other words, you can't change the past in a way that would create a contradiction. This principle is supported by some interpretations of quantum mechanics but remains unproven. Imagine a future where time travel is possible and people can visit different eras as tourists. While this idea is popular in fiction, it raises many practical and ethical questions. How will we prevent people from changing history? What rules would govern time travel? For now, these questions remain hypothetical, but they're fun to consider. Science fiction is full of creative solutions to time travel paradoxes. Some stories use parallel universes, while others rely on self-consistency or time police to keep history on track. These imaginative tales inspire real scientists to think about the challenges and possibilities of time travel, even if the solutions are more fiction than fact. If time travel were possible, it would raise serious ethical questions. Should we allow people to change the past? What responsibilities would time travelers have? Could time travel be used for good, or would it create more problems than it solves? These questions highlight the need for careful thought and regulation if time travel ever becomes a reality. Scientists continue to explore the mysteries of time and the possibility of time travel. Advances in physics, astronomy, and quantum mechanics may one day reveal new insights or even make time travel possible. For now, researchers are focused on understanding the fundamental nature of time and testing the limits of our theories. While we can't hop into a time machine just yet, time travel effects are already part of our daily lives. Technologies like GPS rely on time dilation corrections, and experiments with atomic clocks continue to push the boundaries of our understanding. These real-world applications show that the science of time travel isn't just fantasy, it's part of our modern world. Time travel pushes the boundaries of what we think is possible. It challenges our understanding of physics, causality, and the universe itself. Whether or not time travel ever becomes a reality, exploring these ideas expands our imagination and inspires new discoveries. The journey to understand time is as important as the destination. Throughout history, scientists have devised clever experiments to test the nature of time. From the Hayfel-Keating experiment with atomic clocks on airplanes to modern tests with particle accelerators, these studies have confirmed many predictions of relativity. Each experiment brings us closer to understanding the true nature of time and the possibilities of time travel. Mathematics is the language of physics, and it plays a crucial role in our understanding of time travel. Einstein's equations, quantum mechanics, and other mathematical models allow scientists to explore the possibilities and limitations of time travel. While the math can be complex, it provides a framework for testing ideas and making predictions about the universe. The desire to travel through time is a testament to human curiosity and our quest to understand the universe. Whether through science, philosophy, or storytelling, we continue to explore the mysteries of time. This curiosity drives innovation and discovery, pushing us to ask new questions and seek new answers. Let's recap what we've learned. Time travel is rooted in real scientific principles like relativity and time dilation. While traveling to the future is possible in limited ways, backward time travel faces enormous challenges and paradoxes. Theories like wormholes, cosmic strings, and the multiverse offer intriguing possibilities but remain unproven. The science of time travel continues to evolve as we learn more about the universe. Time travel remains one of the greatest mysteries in science. While we've made incredible progress in understanding time, many questions remain unanswered. Will we ever unlock the secrets of time travel? Only time will tell. Until then, the search for answers continues, inspiring scientists and dreamers alike. In conclusion, the science behind time travel is a blend of rigorous theory, creative imagination, and ongoing discovery. While we may not have time machines yet, the journey to understand time continues to push the boundaries of science and inspire new generations. Thanks for joining us on this exploration of one of the universe's most fascinating mysteries.